So in this lab 7, let's start with that. We talk about something about the behavioral modeling, which is a little bit intense compared to the data flow modeling that we have learned already. So we start. I think there are 4 sections, like 4 part of this behavioral model that you need to understand clearly in order to successfully model or the processor, the control unit in your project 2. First, let's look at the HDL, hardware language paradigm. Right, this is a language, software language, of course, but there is a difference between general programming language like C or Java, as we know. Essentially, HDL, all the HDL, like we are running Verilog, there is another standard called VHDL. They all are a parallel language. We'll see what we mean by parallel language. So the following parts are always executed in parallel, though they can be written in sequence on that if you look at the Verilog code, but they executed in parallel. Like all the instantiation of any module, they actually get executed in parallel, and all the initial block you write, like there can be multiple initial blocks defined within one module, all of them will be executed in parallel. All the always blocks are executed in the parallel, like that's in the same module across different module, whatever, how many numbers of always are always executed in parallel. All the assignments as statement, they are all parallel. There is a non-blocking assignment, which is kind of, instead of equals, it is kind of stating a less than an equal sign. That is called a non-blocking assignment. Let's say A non-blocking assigned B plus C and D non-blocking assigned A plus B. They will be executed in parallel. Okay. Instead of, if we write some statement like A equal B plus C in Verilog itself and D equal to A plus B, they will be executed in sequence. So D equal to A and B, that evaluation is actually blocked by A equal to B plus C for the blocking assignment operator. But if we use a non-blocking, these two assignment, A non-blocking assigned to B plus C and D non-blocking assigned to A plus B, they will be executed in parallel. Okay. Now, let's say this is a little bit just to understand what goes on inside the simulator and this parallel paradigm. What we want to do here, just make some analogy with some existing parallel programming languages like API, message passing interface, like threading, stuff like that. You might not be actively programmed on that, but once you actually do study them, it will make probably more senses. But I'll try to make you understand these from the Verilog perspective. Okay, so let's say I have a ALU test bench. Okay, so far we have dealt with one instantiation of ALU, but let's say there are 2 of them instantiation of ALU. What you can think of, by the way, this is not exactly what is done in reality inside the Verilog simulator, but we can at least model them like this to understand their operation. They're kind of very much similar. Okay, so as soon as there is a process, okay, in the there is a program, right, running this simulation. Let's say the program is ALU test bench. Now, as soon as we instantiate one of the ALU, it actually fork or create a new process, ALU instance 1. Then next it sees, okay, I have another instantiation of ALU, name instance 2, so it fork or create another process, ALU instance 2, and they actually communicate with each other with some communication mechanism. Okay, so what they communicate, ALU.TB communicate, let's say, the value of OP1, OP2 and operation to this instance. Of course, this dot dot actually is exactly the port connection of the operands and operation and result, etc. And ALU instance gives back the result on that. Okay, and OP1, OP2 also can be passed if they're connected like that to the ALU instance, and they will push back the result. The core part to understand is that these two are happening simultaneously in parallel. Okay, so as soon as this guy issues a new OP1, OP2, OPRN to both of them, they are evaluated in parallel to each other. Okay, in time, in execution time, and they both simultaneously put back the result to the ALU-TB. Okay, so this is a concept you need to very used to, familiar with, just to understand like what the behavior of the simulator itself. Okay, next what we do, let's say I have a module and I have like two initial blocks, like initial block 1, initial block 2. We can think of, well, I am spawning a thread. It's a new, we know, if you study the operating system, thread is basically almost like a new process, but it can access all the data. It accesses the data space of its parent process. Okay, it uses the same. Let's say there is a variable a here in the sample process or parent process. Then in it, this block, threaded block, actually can access that a directly. On the other hand, in the MPI, data space is totally different from each other. So if there is a variable a, this guy really cannot access a directly. If ALU.TB wants this guy to access the variable a, it need to pass that variable to this process or this ALU instance. Okay, the thread is something like it's a similar to the process, but data space is the same. So whatever data is here, those two can access this directly, no problem. Okay, so this init block, we can think of this is a spawning threads, and then in these two threads are executed in parallel, and whatever you write here inside this block, they are executed absolutely in parallel from the execution time viewpoint. Now let's look at some complex thing. Okay, let's say we have a module called sample, which let's say C and D an input and E, F, A, B, M, N are output. Now if we do an assignment, E equals C plus D and K equals C plus D, it's basically will spawn threads from that. Okay, it spawns thread, but also there is a dependency. C equal to C plus D and K is depending on E. So these two thread will basically kind of start passing this variable E from each other. So execution of this will blocked by this one. Okay, so it will as soon as it actually evaluates a new E, only then after this guy will be evaluated. Okay, now there is always block one C or D. If C or D changes, then we spawn like two threads, let's say. Now this is blocking assignment. Okay, so nothing magic. This is A equal to C plus D. It will be evaluated first, and then D equal to A plus D. Then it will take the value of D and evaluate D value here. But the block 2, we have a non-blocking assignment here. M is the same thing. C plus D. This is A plus D. This is like M plus D. We take this value and plus 1. Okay, but they will be non-blocking. Since we use the non-blocking assignment here, it will be again spawned into two threads. Okay, assignment 2 of 1 and assignment 2 of 2, and they will be evaluated independent from each other. So that means essentially what value we get on A and D, it won't be same as for the M and N, though the operation is kind of similar, and from the coding perspective this is c plus d and this is previous value of the previous variable plus d, and this guy is previous variable plus d, but they won't be essentially similar. We'll see that in the demo. Okay, so now what we do, we'll go back to our little this model sim and experiment this behavior. Alright, so to do this lab 7 experiment, what you need to do, you go and download from the canvas the source code for lab 7, and you create a project around it, of course, and I have created that. So you got the similar project definition: v, lab 7, test bench, ALU, and sample. This is the same sample as we saw in the slide, the same code. And ALU.v is basically, I have taken the data flow model, and we have a test bench here. So here what we want to do, the test bench is like we are instantiating two of the ALU, which basically we are passing in same operation and operands, but we are observing the result back from on the two different net, rnet1 and rnet2, and then we of course instantiate this net e sample instance, which c and d the input, we are passing the operand 1 and operand 2, and then we do some operation there from the ALU perspective. This is the same test bench as ALU, but there we are interested in seeing this behavior of the sample instance, which is same as the slide we described. Like we have this two assignment which will be blocking. This is blocking assignment and non-blocking assignment, and we'll of course do the ALU behavior as well in parallel instantiation. Now what we do, all need to do is a compile, and then we go and load the test bench. So we'll load it. Okay, and why it is not okay. I should get some okay. Is there a problem in loading? It should load, no problem at all. All the compile was successful. That's okay. Warning should be okay. Let's see why it is not getting the object values there. Okay, let's try to simulate it. Let's simulate. Okay. And oh, we get back something here. Okay, we're looking for to observe these nets, right? Okay, I will add them to the wave. Operands, and then we'll observe the result it as well to wave. Okay, and we'll observe this net over here, and let's change the radix of all of them to decimals. Radix to decimals, so that makes sense. Okay, now what we do, we simulate all. Stop simulation. Okay, simulate all. Oh no, reset. Okay, I need to do that. Okay, and now simulate all. Okay, Here it goes. Now we have this waveform. Let me just try to explain that a little bit from the behavior perspective of this. So remember, let's look at the ALU part first. Okay, so we are interested in these two nets, net 1, net 2. So the part observed we need to do is this: we are passing the operands, same operands and same operation to both instances of the same ALU module, and they should generate the result in parallel simultaneously. See, they are in the time steps, they are in fact generating the same result across the time at the same time in parallel. See, they are, so of course they are being executed in parallel. Okay, now observation from here, let's take this one. Okay, for the sample, remember the sample, let's look at that. E equals C plus D and F equals E plus D. So which means C plus D, we are stating that, so we are interested in these two nets. Now in this cycle it is 15 and 2, so of course 15 plus 2 17, and then F is E plus D, 17 plus 2 is 19. We get that. Okay, now we see A and B. A and B code is A equal to C plus D and B equals A plus D. So first this will be evaluated, then this will be evaluated. So let's look what is there. Okay, so we have 15 2 C and D, then A equal to 15 plus 2 17, B equals 15 plus 17 plus 2 A plus D is 19. We have the result. Now for the non-interesting part is the non-blocking. M equal to C plus D and N equals M plus D, but it is a non-blocking assignment. Let's look at the behavior. This is interesting. So M, we get 17, of course, because it is assigned to be like 15 plus 2 17. Now we think that, well, then since N equal to M plus D, it should be 19, but it is 22. Why? Because the N here is being evaluated in parallel with M. So at the evaluation time, the value of M is basically this one. It is coming from the previous cycle, which is 20, right? It is not changed at this point. It is just started changing this point, right? So when N is being started evaluated, it picks up the previous value of the M, because M and N are being evaluated in parallel. Okay, so it will go and take 20 plus 2 as 22. Okay, so but you might want to say that, well, if they're not in parallel, A and B not in parallel, if they are evaluated sequentially, then how come they are actually changing at the same time? Okay, so here is a trick. The point is that it is being evaluated at the same time. From the simulation perspective, it is changing at the same time, but the value of B is depending on the value of A. So A being evaluated first and put a timestamp, okay, it is changing at this, and B is then changed. Okay, B is then changed, but it is assuming the change duration, the time to change between A and B, the value of A flows to the B, that delay is 0 delay. Okay, so we evaluated at value of A, and that value is being propagated to evaluation of value B. That delay is essentially 0, propagating the result of A to evaluation of the B. So that's why they are on the same timeline. Okay, the 0 delay. If we introduced actually a delay, we can see actually B shifted its evaluation. But here for the non-blocking, it's truly parallel in sense, because this value of M is not propagated to the n evaluation, but n evaluation instead is taking whatever is existing at this evaluation time point, and which is 20 plus 2, it is 22. Okay, so hopefully this makes sense to you. If you have any question, please ask me in the class, and I'll try to re-explain this all together. Okay, so good luck with this.